Okay, good evening to all. Today I am going to start with the definition of similar matrix. So when we say two matrices are similar, so we say there are two matrices A and B. So definition, suppose we have a two square matrix A and B. We say that two square matrices A and B are similar. So when we say two matrices are similar, if there exists another invertible matrices, there exists an invertible matrix. Again, n by n invertible matrix we call capital P, such that they satisfy the relation one matrix, that is P equal to B equal to P inverse AP. If we write B equal to P inverse AP for some P invertible matrix, then we say A and B are similar. So we say two matrices are similar, then there is an invertible matrix P such that B equal to P inverse AP, then A and B are similar. Okay, now we saw some properties of similar matrix. Okay, so the properties. So suppose we have two similar matrix, they have a same characteristic polynomial. Okay, so properties of similar matrices. Properties. So what is the first property? The first property says the characteristic polynomial of similar matrices are same. Okay, that is the characteristic polynomial of similar matrices are same. Similar matrices are same polynomial, are same. Why? Okay. Now, what is the characteristic polynomial of A? So that is why, because suppose we take determinant of A minus xi. So this is a characteristic polynomial of A. So we start characteristic polynomial of the matrix A is nothing but determinant of xi. Or we start with the characteristic polynomial of B. It's not an issue. Okay. So B, we start with the characteristic polynomial of B by the definition determinant of B minus xi. Now, suppose we take A and B are similar. We use the notation A is similar to B. So implies what? There exists P inverse, that is a matrix P, such that B equal to P inverse AP. So similarly, we can write A equal to, we multiply P first and then P inverse, we get same thing, everything same. So either we can write B equal to P inverse AP or A equal to BP P inverse. Anyway, so now we take two matrices A and B are A and B are similar. Now we have to show that the characteristic polynomial of A and then the characteristic polynomial of B are same. So first we start with the characteristic polynomial of B. So that is nothing but determinant of B minus x into I. Now this is equal to B can be written as, since B is related to similar to A, therefore P is nothing but P inverse AP minus x into identity matrix. So identity can be written as P inverse into P. P inverse into P is always identity. Any matrix is product with the inverse is identity. Therefore, the identity matrix can be written as P inverse P. Okay. Now, we can take P inverse from the left hand side and then P from the right hand side. Therefore, the remaining inside we get minus A minus xi into determinant. So now we say three matrix. One is P inverse, another one is A minus xi, another one is P. So determinant of the product of this matrix. And we know the properties of determinant. Determinant of AB equal to determinant of A into determinant of B. Therefore, apply the properties of determinant of the product of the matrix. Here we get equal to determinant of P inverse into determinant of A minus xi into determinant of P. But determinant of P inverse is nothing but 1 by determinant of P. Okay, so that is standard result. So determinant of A inverse is nothing but 1 by determinant of A. We have to use this result. We can easily prove this result by applying. So we know that A into A inverse equal to identity for any invertible matrices. Now apply the determinant both side. Therefore, determinant of A into A inverse equal to determinant of the identity matrix is 1. Now apply determinant of AB is nothing but determinant of A into determinant of A inverse. Now keep the determinant of A inverse and then divide this 1 by determinant of A we get. So therefore determinant of A inverse is nothing but 1 by determinant of A. Therefore we get the determinant of P inverse nothing but 1 by determinant of P into determinant of A minus Xi into determinant of P. Since P is an invertible matrix, therefore the determinant of P is non-zero number. Therefore we can divide. Now we can cancel this determinant of P. We get determinant of A minus Xi. So this is nothing but the characteristic polynomial of A. Characteristic polynomial of the matrix A. Therefore, we start with the characteristic polynomial of B. Now we prove that this is equal to characteristic polynomial of A. Therefore, the similar matrices have same characteristic polynomial. So once the same characteristic polynomial, therefore same root, same eigenvalues. Okay, because both are same polynomial. Therefore, the corollary of this theorem, the eigenvalues of similar matrices are same. Okay, so maybe the second property, the eigenvalues are the characteristic roots. The eigenvalues of similar matrices are same. Because the characteristic polynomial is same, therefore the roots are same. Therefore the characteristic roots are eigenvalues of similar matrices are same. Now once the eigenvalues are same, therefore sum of the eigenvalues is nothing but trace of one matrix. Therefore if A and B are similar, then the trace of A should be equal to trace of B. Trace of the matrix A should be equal to trace of the matrix B. Okay, when provided A is similar to B. Okay, if A is similar to B, then the trace should be equal. Even if you take the determinant, so again determinant is nothing but product of the eigenvalues. We know that the eigenvalues are same. Therefore, determinant of the matrix A is equal to determinant of the matrix B whenever A, B are similar. So A is similar to B, then the trace are equal, then the determinant also equal, and then eigenvalues are also equal. So these are all very important properties of similar matrices. Okay. Now suppose we come to the next one. Suppose we cannot say, suppose a matrix A, suppose we have two matrices A and B. So note, we can say the converse need not be true. So what is the converse? Suppose two matrices A and B, the trace and the determinant of equal, but we cannot say A and B are similar. Okay. So note, suppose we have a matrix, two matrices. We can find two matrices. So we can find two matrices A and B. We can find two matrices A and B with the trace of A equal to trace of B and determinant of A equal to determinant of B, but A is not similar to B. A is not similar to B. But if A and B are similar, then trace and determinants are equal, but the converse need not be true. That is, you can find two matrices. The trace of two matrices are equal and the determinant of two matrices are equal, but A is not similar to B. Okay, we can always find such a matrix. Therefore, the converse need not be true. It's very important note. Okay. Okay. Now, maybe we discuss some theorem. Suppose we have two matrices. Okay, So maybe we state as a theorem. Suppose 0 is the one of the eigenvalues of the product of the matrix. This need not be similar. Okay, suppose I take any matrices. Okay, suppose for any matrix A and B, for any n by n matrices A and B, A and B, the following are equivalent. The following statements are equivalent. The following are equivalent. So what is the first statement? I am saying that. So if suppose 0 is an eigenvalue, 0 is an eigenvalue of the matrix, the product eigenvalue of AB. If suppose 0 is the one of the eigenvalues of the product of the matrix AB, then we say second one is either A is singular or B is singular. Singular means what? Not invertible. So A or B is singular matrix. So singular matrix means what? Determinant should be 0. Okay, and 0 is an eigenvalues of BA. So 0 is an eigenvalue of the matrix B into A. So this is a theorem. Suppose 0 is an eigenvalues of AB, then we have to prove that either A is singular or B is singular. Suppose if I assume A is a singular or B is a singular, we have to show that 0 is an eigenvalues of BA. Okay, so this simple proof. So maybe we can simply say proof. So since they given that 0 is an eigenvalues of AB, therefore what is the determinant of AB? So determinant of AB is nothing but product of eigenvalues of AB, but we don't know other eigenvalue, but we know one eigenvalue is 0. Therefore 0 into anything is 0. Therefore determinant of AB equal to 0. Because we are saying that 0 is an eigenvalue. 0 is an eigenvalue of AB implies that the determinant of AB should be 0, because determinant of AB is nothing but product of the eigenvalues of AB. We know one of the eigenvalues is 0, therefore product is 0. And we know the properties of determinant of AB is nothing but determinant of A into determinant of B. This is equal to 0. Since the product of two numbers, namely determinant of A and the determinant of equal to 0, then one of the number must be 0. So implies either determinant of A is 0 or determinant of B is 0. Okay, so that is determinant of A is 0 means what? A is singular. That is implies that either the matrix is singular, A is singular, or B is singular. Singular means what? Is not invertible. So either A is singular or B is singular. Now we proved 2. If you assume 0 is an eigenvalue of AB, then either A or B is singular. Now suppose assume that either A is singular or B is singular, then we can easily show that 0 is an eigenvalue of BA. So proving 0 is an eigenvalue of BA, it is enough to prove that the determinant of BA is 0, because product of the eigenvalue is nothing but determinant. Now we prove the second statement implies the third statement. So we are assuming that either A is singular or B is singular. Now what is determinant of BA? By the definition of by the properties of determinant, so this is nothing but determinant of B into determinant of A. But we assume that either A is singular or B is singular. Therefore, one of the number must be 0. Either determinant of A is 0 or determinant of B is 0. Anyway, the total product is always 0. Because we assume that either A is invertible, A is singular or B is singular. Now we get the determinant of BA equal to 0, but determinant is nothing but product of the eigenvalues. We get the product is 0. Therefore, 0 is the one of the eigenvalue. Therefore, 0 is an eigenvalue of the matrix BA. Now we prove the last part. 3 implies 1. Equivalence is what? We have to assume one statement, we have to prove another statement. Now assume the third statement. What is the assumption? 0 is an eigenvalue of BA. What we have to prove? 0 is an eigenvalue of AB. So assume 0 is an eigenvalue of the matrix BA. What we have to prove? To prove A0 is an eigenvalue of AB. So it's nothing but we have to prove the determinant of AB is 0. So what we know, 0 is an eigenvalue of BA. That means what? Determinant of BA should be 0. But determinant of BA is nothing but determinant of B into determinant of A equal to 0. But determinant is a real number. But we know in the real number AB equal to BA. Therefore, we can write this nothing but first we have to write the determinant of A into determinant of B. Because determinant of A and the determinant of B are numbers. Therefore, we can rewrite this. Now again apply the properties of determinant. Determinant of A into determinant of B. Therefore, determinant of AB is 0. Since determinant is 0, therefore 0 is an eigenvalue of AB. Therefore, 0 is an eigenvalue of the matrix AB. Okay, suppose, so therefore we proved all the part. If 0 is an eigenvalue of AB, then either A or B is singular, or 0 is an eigenvalue of the matrix BA. Now we are going to prove the matrix AB and the BA have same eigenvalues, not eigenvectors, same eigenvalue. Suppose lambda is an eigenvalue of AB, then the lambda is also an eigenvalue of B. So that is important theorem. So therefore, AB any matrix need not be similar matrix. If AB any matrix, okay, then same eigenvalues. So maybe you state as a theorem. The theorem says, suppose we have two matrices A and B. For any n by n matrices A and B, for any n by n matrices A and B, the matrices AB and BA, the matrices, the product AB and BA. In general, AB not equal to BA, okay? In matrices, AB need not be equal to BA. That's why we talk about AB and BA. So the matrices AB and BA have same eigenvalues, But eigenvalues may be different. But eigenvectors may be different. Eigenvalues are same. So what is the proof of this? Suppose we start with the eigenvalue of AB. We have to prove that eigenvalue should be an eigenvalue of BA. So proof. Suppose we know that if suppose 0 is an eigenvalue, we already proved in the previous theorem. If suppose 0 is an eigenvalue of AB, then 0 is an eigenvalue of AB. Okay, that is a simple proof. Suppose if we take some non-zero eigenvalue, okay, suppose let lambda be the non-zero eigenvalues of AB. Let lambda be a non-zero eigenvalue, because if it is zero eigenvalue, we already know. So suppose let lambda be a non-zero eigenvalue. If you take one arbitrary eigenvalue of the matrix AB, then we have to prove that lambda is also an eigenvalue of BA. So by the definition of lambda is an eigenvalue, that means what? There is some non-zero vector V in B such that AB into V equal to lambda times V. That is the definition. Okay. So lambda is an eigenvalue of A means what? AB equal to lambda V. There is some V non-zero such that AB equal to lambda V, then V is an eigenvalue. This lambda is an eigenvalue. This V is an eigenvector corresponding to the eigenvalue lambda. Okay, so this is the definition of lambda is an eigenvalue. This V is an eigenvector corresponding to the lambda. Now here lambda is an eigenvalue. Therefore, there is some non-zero vector. So eigenvectors are always non-zero. So this has happened. So there is a V non-zero in B such that AB into V equal to lambda times V. Now apply B both sides. Therefore, B into AB of V equal to B of lambda V. Now apply B both sides. And we know that B is a matrix. Already we know that every matrix is a linear transformation. Therefore, this lambda is a scalar. Therefore, we can take lambda is outside because B is a linear transformation. We get B into V. Now here we can apply the associative property. Okay. Therefore, this is AB into BA. BA into BV. So therefore BA times some vector BV equal to lambda times BV. Therefore, if this will look like some BA times X equal to lambda times X. Therefore, lambda is an eigenvalue. Okay, this BV is the eigenvector corresponding to the lambda for the matrix BA. Okay, anyway, we get a relation like this. Some BA into vector equal to lambda into that vector. Therefore, lambda is an eigenvalues of AB. So BA. So therefore, from this we can conclude that lambda is an eigenvalue, value of BA. Okay, we start with the lambda is an non-zero eigenvalues of AB. Now we prove that lambda is an eigenvalues of BA. Therefore, if you take any matrix, the eigenvalues of AB and the eigenvalues of BA both are same, but the eigenvectors may be different. Okay? Because look at the first AB. So here V is an eigenvector. So in this case, V is an eigenvector, but in this case, B into V is an eigenvector. Therefore, eigenvectors may be different, but eigenvalue is always same for the matrix AB and B. Okay? It's very important. And then if you take matrix A and then if you take the transpose of the matrix, both have same eigenvalue. So that is the next point. Both A and A transpose have the same eigenvalue. Okay. So maybe I can write the point. A and its transpose, A transpose, have same eigenvalue. Have the same eigenvalues. Okay, that's why determinant of A equal to determinant of A transpose, trace of A equal to trace of A transpose, because both A and A transpose have same eigenvalues. That's why trace of A equal to trace of A transpose or determinant of A equal to determinant of A transpose. Okay, so this is very important point. Suppose if you know A is invertibly meant what? All the eigenvalues of A should be non-zero. Okay, that is, if A is invertible matrix, if and only if all the eigenvalues are non-zero. All eigenvalues of A are non-zero, because product of the eigenvalue is determinant. Okay, if determinant non-zero, we can say it's invertible. So all the eigenvalues of A are non-zero. Again, if a matrix, in a matrix all the eigenvalues are non-zero, then such a matrix is invertible matrices. Okay, this is very important. Suppose we know the eigenvalues of A, we can easily say the eigenvalues of A inverse. Okay, that is, suppose A is invertible and we know the eigenvalues of A. So A is invertible and we know the eigenvalues of A. So A is invertible. Okay. And then the inverse also invertible, because A inverse whole inverse is nothing but A. And what is the eigenvalue? Suppose A is invertible, and suppose I take lambda 1, lambda 2, etc., lambda k or lambda n are eigenvalues of A, then the eigenvalues of A inverse, then the eigenvalues of the inverse matrix, eigenvalues of A inverse are, just to take the reciprocal, 1 by lambda 1, comma 1 by lambda 2, comma 1 by lambda 3, and so on, 1 by lambda n. Because all the eigenvalues are non-zero, because it's invertible, therefore all the eigenvalues are non-zero, therefore we can define 1 by lambda 1, 1 by lambda 2, etc., 1 by lambda n. So these are all eigenvalues of A inverse. And we know the positive power. So what is the positive power? If you know lambda 1, lambda 2, etc., lambda n are the eigenvalues of A, then what is the eigenvalues of A power k? Is nothing but lambda power k, etc. So maybe I can write another point. Okay, suppose if lambda 1, lambda 2, etc., lambda n are eigenvalues of A, are eigenvalues of A, then for any positive k, then for any positive number, because we cannot say about the negative number, okay, or zero number. Okay, suppose for any k greater than 0, the eigenvalues of a power k, the eigenvalues of the matrix a power k are lambda 1 power k, comma lambda 2 power k. Just raise the power to each eigenvalues, lambda n power k. Why? This is again simple proof. Suppose if you take one eigenvalue lambda for a, we have to prove that lambda power k is an eigenvalue. So simply suppose we take a b equal to lambda v. That means what? We assume that lambda is an eigenvalue. Therefore, there is some v such that a b equal to lambda v. Now apply a k times. Therefore, we get a power k of v. That is suppose you apply k minus 1 times. Therefore, a power k minus 1, or if you take so okay, better first you have to apply 1 times. Suppose I am applying a both side, so what you'll get? A into a square. So that is a of ab equal to a of lambda v. Now a is a linear transformation because it's a matrix. Therefore, we can take lambda outside, we get av. Now maybe we call this equation number 1. Now we know that ab equal to lambda v. Therefore, this is lambda, and ab is nothing but again lambda v. So lambda into lambda, lambda square v. And here a into a square v. Therefore, a square is equal to lambda square v. Therefore, lambda square is an eigenvalue of a square. So similarly, in general, we can say a power kv equal to lambda power kv. Therefore, lambda power k is an eigenvalue of a power k. So if you know eigenvalues of a, we can easily say eigenvalues of the powers of a, for positive powers of a. Why we cannot talk about the negative powers? Because if suppose 1 lambda is 0, we cannot define 1 by lambda. But if given that a is invertible, then we can say for any powers we can talk about the eigenvalues of a power k, where k is anything. To know the a is invertible or all the eigenvalues are non-zero. Otherwise, we cannot talk about the reciprocal of the eigenvalues. So we can say we can define the reciprocal of the eigenvalues only when a is invertible. So these are all some important properties of uh, eigenvalues of a matrix, both A and A transpose, and then powers of A. Okay. Now, if you take any matrix, the matrix AB and BA are similar. Okay. Provided one of the matrix is non-singular. So maybe state as a theorem or note. So theorem. Suppose we have two matrices for any n by n matrices A and B. Suppose we have two matrices A and B, and assume that one of the matrices is non-singular. Either A is non-singular or B is non-singular. Okay, that is, and if A or B is non-singular. Non-singular means what? Invertible. Either A or B is non-singular, then the product of the matrix AB and BA are similar. Then AB and BA are similar. Why? That means what? We can find such an invertible matrix such that one matrix AB can be written as inverse of other matrix. That is, suppose assume that either A or B is singular, right? So without all of generality, we assume that A is non-singular. A is non-singular. That means what? Inverse exists. Suppose we assume that A is non-singular. Then we have to prove that AB and BA are similar matrix. So that means what? We have to write AB equal to some matrix P inverse into BA into P. We have to find such a matrix P. So what we have to take? Or we can write this form. No need to write AB equal to, we can write BA equal to also. can adjust. Okay, BA equal to P inverse times A B into P. So choose A P equal to A. Therefore, what is P inverse is nothing but A inverse. Therefore, now apply this side. P inverse is nothing but A inverse AB into A. Now we can A inverse A cancel, we get BA. That side, that is in the left hand side. Okay, therefore, if A is, we can say, suppose assume that A is singular matrix, then A, B and B, A are similar matrix. Suppose similarly, if assume B is non-singular, then we can write A, B equal to P inverse B, A, P. In that case, we take P equal to B. Because its inverse exists, that's why we are taking this. Therefore, the AB and BA are similar matrix if one of the matrix A or B is singular, non-singular matrix. One of the matrix non-singular, then the product AB and BA are similar matrix. And if you know similar, then we can know about the trace and determinant. Even not only trace and determinant, the rank of the matrix also same. That is, if A and B are similar matrix, then the rank of A equal to rank of B. That is very important thing. Okay, maybe I can write here. Note, if A and B are similar matrix, if A and B are similar matrix, then the rank of A equal to rank of B. Rank of the matrix A equal to rank of the matrix B. So this happens only when A and B are similar matrix. But converse need not be true. Suppose rank of A equal to rank of B, we cannot say A and B are similar. Okay, for similar matrix, ranks are equal. Similarly, for similar matrix, determinant is same, trace is same. But if trace is same, determinant is same, we cannot say A and B are similar. Okay, and that's point we have to keep in mind. Okay, now we move to the definition of diagnosable. When we say a matrix is diagnosable, if that matrix is similar to a diagonal matrix. A matrix has to be diagonalizable matrix if that A is similar to a diagonal matrix. That's the definition. Okay. So definition for diagnosable. Okay. So with the definition, a square matrix A capital A is said to be diagnosable. Is said to be diagnosable. Said to be diagnosable if there is a invertible matrices P, so there exists an invertible matrices Q or P, invertible matrix P such that the P inverse AP is diagonal. Is a diagonal matrix. Is a diagonal matrix. That is actually what we are saying here. So that is, we say A is diagnosable if A is similar to diagonal matrix. A is similar to a diagonal matrix. A matrix is similar to a diagonal matrix, then we say that matrix is a diagnosable matrix. Okay. So diagonal matrix means what? So don't confuse this diagonal and the diagnosable. Okay. Not all the diagnosable matrices are diagonal. Diagonal matrices are diagonal. Okay. So keep in mind. So that is what we can say. So this P inverse AP should be D. So what is this D actually? D is nothing but only diagonal elements are non-zero, all others are 0. So what are the diagonal elements is nothing but just the eigenvalues of A. So that is lambda 1, lambda 2, etc. Lambda n, all others are 0. So we get the diagonal matrix. The diagonal entries lambda 1, lambda 2, etc. lambda n are nothing but the eigenvalues of the matrix A. Okay. So where this lambda 1, lambda 2, etc., lambda n are eigenvalues of the matrix E. Okay. This is a definition of diagnosable. Similarly, we can say for any linear transformation. Okay, any linear transformation from finite dimensional vector to finite dimensional vector space is to be diagnosable. Maybe I will tell later. Okay, so that definition. So this is a definition for a matrix is said to be diagnosable if there is a invertible matrix P such that P inverse AP is a diagonal matrix. Now we have some characterization to check a matrix is diagnosable or not. Okay. Okay. Suppose A is diagnosable if and only if A has n linearly independent eigenvectors. So before that, I state the theorem. Suppose A is a matrix. So maybe state the theorem. This theorem is very important. Suppose A is any matrix. Suppose lambda 1, suppose lambda 1, lambda 2, etc., lambda k are distinct eigenvalues. Distinct eigenvalues of an n by n matrix. But matrix is n by n matrix. We can take, suppose we get k distinct real numbers, may other k distinct eigenvalues, maybe other eigenvalues are same. Okay, so that's why I'm taking k. Not instead of taking n, I take k. So eigenvalues of an n by n matrix, not k by k matrix. So here k is less than or equal to n. Okay, so n by n matrix A, then the corresponding eigenvectors. So if we take any eigenvalue, we can find the eigenvector, right? Suppose lambda is an eigenvalue means what? There is a v such that AB equal to lambda 1b. Then this v is called the eigenvector corresponding to the eigenvalue lambda. Suppose lambda 2 is an eigenvalue, there is another vector, maybe you can take w equal to lambda 2 w. So this w is called the eigenvector corresponding to the eigenvalue lambda. So these eigenvectors are linearly independent. So if you take distinct eigenvalues, then the corresponding eigenvector, then the corresponding eigenvectors are linearly independent. Corresponding eigenvectors, maybe we call some name. V1 is eigenvector for lambda 1. V2 is an eigenvector corresponding to lambda 2 and so on. Vk is an eigenvector corresponding to lambda k are linearly independent. If you take distinct eigenvalues, the corresponding eigenvector should be linearly independent. Now, suppose in a n by n matrix, all n eigenvalues are distinct. Then all n eigenvectors also linearly independent. In that case, A is diagnosable. That is the next theorem. Suppose all the eigenvalues are distinct, then it's linearly independent. Otherwise, we can say, suppose eigenvectors are linearly independent for n by n matrix. Okay, suppose the theorem says, suppose A is an n by n matrix, let A be an n by n matrix. N by n matrix, then A is diagnosable. Then the matrix A is diagonalizable. Diagnosable if and only if A has n linearly independent eigenvectors. So A has n linearly independent eigenvectors, not eigenvalues. Okay, so eigenvalues are just a scalar. We cannot talk about the linearly independent there. Okay, so we can talk about linearly independent only for vectors. Therefore, suppose if A has n linearly independent eigenvectors, then we say A is diagnosable. N linearly independent eigenvectors. So a very important characteristic for one of the characteristics for diagnosable. If a matrix is diagnosable, the matrix has n linearly independent eigenvectors. Okay. Now, but in general, not all matrices are diagnosable matrices. Some matrices are not diagnosable. So even more we can say, if you take any nilpotent matrix, non-zero nilpotent matrix is not diagnosable. Why? Suppose we take some example. So therefore, the example says not all matrices are diagnosable. There are some matrices which are not diagnosable. Okay, so that is not all matrices are not diagnosable. All matrices are not all matrices are diagnosable. Why? If you take some specific matrix, if you take any nilpotent matrix, non-zero nilpotent matrix is never diagnosable. Nilpotent matrix is diagnosable only when that matrix should be zero matrix. Okay, now we give some example to this. Suppose if we take A equal to 2 by 2 matrix. Suppose A equal to 0, 0, 0, 1. Clearly, this is a nilpotent matrix. Why? Because what is A square? A square is nothing but 0 matrix. Why? Just to check it. So A into A, we get 0, 0, 0. You can easily check. So clearly, actually, I am taking A is a nilpotent matrix. A square is 0. Now, suppose this A is diagnosable. So we are going to show this A is not diagnosable. Suppose this matrix is diagnosable. That means what? There is an invertible matrix. Okay, what is the eigenvalues of this A? So this is upper triangular matrix. Therefore, the diagonal elements are eigenvalues. Therefore, the eigenvalues of A are 0, 0. Now, suppose A is diagnosable. Suppose the matrix A is diagnosable. Then what will happen? By the definition of diagnosable, there exists an invertible matrices. There exists an invertible matrix P. Invertible matrix P. P is also 2 by 2 matrix. We are working 2 by 2 matrix. There exists an invertible matrix P such that P inverse AP should be diagonal, right? But the diagonal matrix contains the diagonal elements are eigenvalues of the matrix, but eigenvalues of the matrix 0, 0. Therefore, the diagonals only the diagonals are non-zero, but here the diagonals are 0, 0 because 0 is an eigenvalue. We get 0 matrix. That 0 is a diagonal matrix, but the diagonal is 0 matrix. So now multiply P inverse left hand side, we get A equal to 0 matrix, which is a contradiction because in A at one entity is non-zero. Therefore, if you assume A is diagnosable, we get 0 matrix, which is a contradiction to our hypothesis A is a non-zero matrix. Therefore, this matrix is not diagnosable. Even in general, if you take any non-zero nilpotent matrix, at least one entity should be non-zero, and then it is nilpotent, it's never diagnosable. That is very important note. Okay, regularly they will ask questions related to this. Nilpotent matrix is never diagnosable except the case A equal to 0. Okay, note. Where you can say a nilpotent matrix is diagnosable only when the matrix is 0, or a non-zero nilpotent matrix never nilpotent. So never diagnosable. A non-zero nilpotent matrix, a non-zero nilpotent matrix never diagnosable. Suppose a nilpotent matrix is diagnosable, then the matrix should be 0. Okay, that is a very important point. Why? Because finally you will get a 0 matrix. Because all the eigenvalues of nilpotent matrix is 0. Okay, that is also one important note. You should remember always. Okay, so the second one is all eigenvalues of nilpotent matrix. All eigenvalues of and often of a nilpotent matrix are 0. 0 is the only eigenvalue for the nilpotent matrix. Why? That is very simple proof. Suppose we take lambda is an eigenvalue of a nilpotent. Suppose as first we take nilpotent matrix. Suppose let A be a nilpotent matrix. Nilpotent matrix. So that means what? A power some k equal to 0. The k may be less than or equal to n, but A is a n by n matrix. A is an n by n matrix. But A is nilpotent means what? A power k should be 0 matrix. For this k may be less than or equal to n. Maybe sometimes equal to n, but should be less than or equal to n. Now we know this. Suppose we take some eigenvalue, lambda. We got to show that that eigenvalue should be 0. Suppose let lambda be an eigenvalue of the matrix E. Now what we are going to prove that lambda should be 0. Since by the definition of eigenvalue, there is some V non-zero vector in the vector Rn, thus linear A is a linear transformation from Rn to Rn because it's a n by n matrix. Therefore, it's a linear transformation from Rn to Rn. Okay. So there is we get some non-zero vector such that AB equal to lambda V. So lambda is an eigenvalue, therefore there is some V such that AB equal to lambda V. And we know that A power k is 0. Now I'm going to apply A both side k times. Therefore we get A power k times V equal to, since A is a linear transformation, therefore we can take, so first suppose I take, first apply A square. Now apply both side A to this equation, we get A square V equal to A of lambda V. Now since A is a linear transformation, therefore the scalar lambda comes out. Therefore lambda times AB. Now again we know that AB is nothing but lambda times V, therefore lambda into lambda square V. Therefore A square V equal to lambda square V. Similarly we can go up to A power k. So therefore A power k equal to lambda power k times V. But A power k is 0, therefore 0 times V is 0. Therefore this side we get 0. So finally what we will get? Lambda power k times V is 0 vector. But we know that V is a non-zero vector. Therefore only possible is lambda power k should be 0. Since lambda is a number, so suppose so lambda power k equal to 0 means what? You are multiplying lambda k times lambda k times equal to 0. So that means our only possible is lambda should be 0. So we start with the eigenvalue lambda. Finally we prove that the eigenvalue should be 0. Therefore, if we take any nilpotent matrix, 0 is the only eigenvalue. All the eigenvalues are 0, 0, 0, 0, n times. Okay. So now, using the second node, we can prove the first one. If we take any non-zero nilpotent matrix, is never diagnosable. Suppose assume that it's diagnosable. Therefore, there is a invertible matrix P such that PA P inverse equal to diagonal matrix, but the diagonal entries are eigenvalues. Again, diagonal is 0, 0, 0. Therefore, we get 0 matrix. So in this case, suppose we assume that diagnosable, then we get a matrix P inverse AP should be equal to diagonal matrix. The diagonal entries are eigenvalue, but we know that the eigenvalues of the nilpotent matrix are 0, 0, 0. Therefore, we get only 0 matrix. Now we can cancel this, multiply P inverse left hand side, both right hand side, we get A should be 0. Which is a contradiction because we assume that A is a non-zero nilpotent matrix. So therefore, a non-zero nilpotent matrix is never diagnosable. It's a very important thing. Now there are some other characteristic there to check matrix is nilpotent or not. Okay, so the important thing, suppose we can say, suppose the eigenvalues are distinct. You know, the n eigenvectors are n linearly independent eigenvectors if and only if it is diagnosable. Suppose we have distinct eigenvalues, then again it's a nilpotent because the distinct eigenvalues means linearly independent eigenvectors. Maybe it's a corollary of this. Maybe we can state. Okay, what is it? Suppose if an n by n matrix have, if an n by n matrix A have n distinct matrix A has n distinct eigenvalues, n distinct different eigenvalues, okay, distinct eigenvalues, not eigenvectors, distinct eigenvalues, then automatically A is diagnosable. Because from n distinct eigenvalues, we know the theorem that the corresponding eigenvectors are linearly independent, n linearly independent eigenvalue, therefore it's a diagnosable. So then A is diagnosable. If a n by n matrix contains n distinct eigenvalues, directly we can say it's diagnosable matrix. Okay. Now, this concept are very useful to find the powers of a matrix. Suppose they give matrix some A, they ask to find what is the A power 100, A power 50, and all. So maybe we'll discuss one problem. So how to find the powers of a matrix? So suppose they given A, so finding A square, A cube, these are all easy. Okay, we can easily multiply A and A. Suppose they ask the highest power. Maybe they will ask A power 50, A power 100, A power 200. They will ask like that. Now, how to find that such a matrix? Now, that is very useful to hear. So, exercise or problem. Suppose they compute A power 100. Compute A power 100. But what is the matrix A? For A equal to some 2 by 2 matrix, or they will give some 3 by 3 matrix. 1, 4, 3, 2. So we have to multiply A 100 times. Then only we know what is A power 100. But there is some shortcut to find the values of A power 100. Okay. So there are two different methods are there. So the simple one is first you find the eigenvalues of the given matrix. So we know the characteristic polynomial, right? Because it's a 2 by 2 matrix, so we can easily write the characteristic polynomial. So what is the characteristic polynomial of A is just x square minus trace. Trace is sum of the diagonal, that is 3 times x plus determinant. What is the determinant? 2 minus 12 is nothing but minus 10, therefore should be minus 10. So we can take this is equal to 0, characteristic equation. Now what are the roots? What are the roots? This is the product of the roots, this is the sum of the roots, therefore 5 into 2. Therefore we can write x minus 5 into x minus 2. No, x plus 2 equal to 0, right? Then only we can get minus 5x plus 2x, we get minus 3x. Therefore the roots are 5 and minus 2. Therefore the eigenvalues of A are minus 2 and 5. Now we have to find a what? Eigenvector corresponding to minus 2, eigenvector corresponding to 5. So how to find the eigenvector corresponding to minus 2? So that is simple. So for lambda equal to minus 2, in that case, what is the eigenvector? So that is, eigenvector is nothing but the solution of A minus 2y into x. X is nothing but you take x, since A is a 2 by 2 matrix, therefore xy. Okay, there we take capital X. A non-zero solution of this equation are called eigenvectors. So what is A minus 2y? So A is nothing but 1, 4, 3, 2. Just to subtract minus 2 only on the diagonal. So what you'll get? So A is, so maybe I can write here A equal to 1, 4, 3, 2. I think so. Yeah. Now if you subtract minus 2, what you'll get? So in place we get, if we take subtract minus 2, we get minus 1, and this is 4, this is 3, 2 minus 2 is 0, and this x, but x is nothing but we take xy equal to 0, 0. Now just you multiply this, what you'll get? Minus x plus 4y equal to 0. Now from the second, 3x equal to 0. Therefore, what you'll get? X should be 0. If x is 0, then y must be 0. Right? So therefore, in that case, you can directly say that minus 4 and then 3. Maybe I did some mistake. Is it correct? No. So we can take 1, 4. Oh, sorry. So nobody is informed. So this actually minus 2 means it should be plus. That means you get add 2. Yes, eigenvalue is minus 2. So therefore, what you'll get? The diagonal elements is 1 plus 2 is 3 here, and the last one is 2 plus 2 is 4. Now look at the both are same, therefore we get only one equation, namely 3x plus 4y equal to 0. Now for what is the value of x and y? We can take any one variable is free variable, and then we can find the other variable. So suppose if fix y equal to 1, we know x. What is x? If you substitute x equal to, or if you take better, I take otherwise, if you take y equal to 3, better. So if suppose you take x equal to 3, or if you take y equal to 3, then what is this? This is 12. If you take this minus 12 by 3 is minus 4. You take any value, so simply I am taking, for simplicity I am taking this. Therefore, the eigenvector corresponding to the eigenvalue minus 2, one of the eigenvector is the vector minus 4 and then 3 is an eigenvector. This is one of the, so for single eigenvalue it has a infinitely many eigenvector. So this is one of those. Okay, so eigenvector corresponding to lambda equal to minus 2. Good. Now again for another eigenvalue lambda equal to 5. So for lambda equal to 5, what is the eigenvector? So for lambda equal to 5, so eigenvector is nothing but the solution of a minus 5 lambda, sorry, 5 times I into x equal to 0. The non-zero solution of this system. So what is a actually? A is nothing but 1, 4, 3, 2. Now we have to subtract minus 5. So what you will get? Minus 4, 4, 3, minus 3 into x is nothing but there are two variables. We take xy equal to 0, 0. Now what you will get? If you multiply these, you get minus 4x plus 4y equal to 0. And then the second equation we get 3x minus 3y equal to 0. Anyway, from this just to multiply divided by 4 or divided by minus 4, we get x minus y equal to 0. And then you divide by 3, we get x minus y equal to 0. Therefore, just we get x equal to y. So both x and y were same value, but should be non-zero. Therefore, better I take 1, 1. If you take x equal to 1, then y should be 1. Or if you take x equal to 2, y equal to 2. Therefore, better a simple case I take 1, 1. So 1, 1 is an eigenvector corresponding to lambda equal to 5. Now once you find the eigenvector, you have to form the invertible matrix P. So it's nothing but just you write the column vector of our eigenvector. So what is the, for lambda equal to, you can take anything. So for lambda equal to minus 2, we get a minus 4, 3. You take here. So minus 4, 3 is the eigenvector. Now for lambda equal to 5, you get 1, 1. So this is our matrix P. Okay. Now since we get a distinct eigenvalue, okay, here the eigenvalues are minus 2 and 5. Therefore, the given matrix A is diagnosable. It's a 2 by 2 matrix. All the eigenvalues are distinct. Therefore, this A should be diagnosable. Therefore, we can get a invertible matrix P such that P inverse AP should be diagonal. But here, how to find that P is nothing but just to write the column vectors are the eigenvectors corresponding to the eigenvalue. Now this is P. Now what is P inverse? P inverse is nothing but, so for 2 by 2 matrix, just you got to, what is the determinant? So determinant is nothing but minus 4, minus 3 is minus 12 is the determinant of P. So what is the formula for P inverse? 1 by determinant into adjoint. So adjoint is nothing but just you have to interchange the diagonals. This is 1 and this is 4, minus 4, and we have to put minus here, right?
Minus 4 minus 3 is minus 7 will it?
Sorry?
Minus 7 will come now, sir.
Oh, sorry. Yeah, thank you. So this is equal to minus 7. Okay, therefore this should be minus 7. So you can easily check that this is inverse or not. Just to multiply P and P inverse, you get identity matrix. Okay. Okay, so we will check quickly. So P inverse is nothing but we can take 1 by 7 outside. What is P? Minus 4, 1, 3, 1, into 1 minus 1 minus 3 minus 4. Now this is nothing but 1 by 7 into, so minus 4 minus 3 minus 7, and this one is minus minus plus 4 plus 4 minus 4 is 0, and this one is plus 3 minus 3 0, and this minus 3 plus minus 3 minus 7 minus 7. So this is a minus, right? So you can multiply minus inside, we get identity matrix. Okay, good. So therefore this is inverse. This is a P inverse. Now we know that the A is diagonalizable, therefore P inverse AP should be diagonal, but the diagonal entries are only nothing but the eigenvalues. Eigenvalues are 2 and 5. Now raise the 100 to the both side. I already said that P inverse AP raise the power any n is nothing but just P inverse A power n into P. Just the power come only in the middle of the matrix. Okay. So now raise the power 100. So you get P inverse AP power 100 is nothing but minus 2 0 0 5 100. So for diagonal matrix, this 100 nothing but just to raise the power 100 to the each diagonal elements. Okay, that is trivial. Therefore minus 2 power 100 minus is a odd, therefore we get just 2 power 100 here. This is 0 and this is 0. Here we get 5 power 100. So this is P inverse AP power 100. But if you take 100 inside, we get P inverse A power 100 into P equal to this matrix 2 power 100 0 0 5 power 100. But we need A power 100. Therefore just multiply this P inverse. Therefore A power 100 equal to, first you cancel this P inverse, therefore multiply by P into this matrix into, you can cancel this P, therefore multiply by P inverse, left hand side, right hand side, we get this one. Now what is P? We know that what is P. So P is minus 4 3 1 1 minus 4 3 1 1, and this diagonal is 2 power 100 0 0 5 power 100. So this P inverse contains minus 1 by 7. You can multiply minus inside, and I am taking the 1 by 7 outside, therefore 1 by 7 times. So I multiply minus, okay, minus is there. Now multiply minus inside, therefore the first row minus 1 1, and the second row 3 4. I think I'm correct. Now this is a 2 by 2 matrix. We can product, right? So we can easily find the product. So this is nothing but 1 by 7 times. So first multiply these two matrices. Therefore what you'll get? Minus 4 times 2 power 100 and then 0, and here 0 5 power 100, and 3 times 2 power 100 plus 0, here 0 5 power 100 times minus 1 1 3 4. So this is equal to 1 by 7 times. Now multiply this, minus minus plus 4 times 2 power 100 plus 3 times 5 power 100. Okay, and this term minus 4 times 2 power 100 plus 4 times 5 power 100, and this one is minus 3 times 2 power 100 plus 3 times 5 power 100, and the last one is 3 into 2 power 100 plus 4 times 5 power 100. So anyway you can stop here, otherwise if you want you can simplify it more. Okay, so depending upon the answer. Okay, suppose in the option they give any value, if you want you can more simplify. So otherwise you can stop this one. So no need to further simplify. Okay, so this is the value of A power 100. This is a value of A power 100. So therefore this character, the diagonalizable concept is very useful to find the powers of any matrix. So here I am taking 2 by 2 matrix. But in the examination, they will ask, sometimes they will ask 3 by 3 matrix. They will ask what is the power of a power 50 or something. Okay. Okay. Now, one more thing, maybe I will ask, say this one. Suppose if you know eigenvalues of A, and if you know eigenvalues of A square, suppose if you know, so they suppose they will ask, maybe I write the problem now. So problem or exercise, they give the matrix A. So A is nothing but some 3 by 3 matrix. So what is the matrix is 5 minus 4 and then 4, 12 minus 11 and then 12, 4 minus 4, 5, 4 minus 4, 5. Suppose they give you 3 by 3 matrix. Now question is, check the matrix is diagnosable or not. So otherwise prove that A is diagnosable. And second thing is, find the eigenvalues of not A but A power 10 plus A power 7 plus 5 times A. So you have to find the eigenvalues of this matrix. So there is some simple trick is there how to find the eigenvalues of these matrices. So suppose first you have to find the eigenvalues. So first you can find the eigenvalues of A. Okay. Suppose the eigenvalues of A are lambda 1 power lambda 1 lambda 2. Suppose we take 3 only for simple case. I am taking 3 eigenvalue lambda 1 lambda 2 lambda 3. Then the eigenvalues of, we know that A power k is nothing but lambda 1 power k, lambda 2 power k, lambda 3 power k. So what is the eigenvalues of 5 times A? You just multiply 5 to the each term. So 5 times lambda 1, 5 times lambda 2, 5 times lambda 3. Okay, now just add the term by term. So correspondingly we got to add this thing. This is one of the eigenvalues of the sum and this one. So for example, in this case, so for suppose A, eigenvalues of A are lambda 1, lambda 2. Suppose I'm taking 2. Okay. So what is the eigenvalues of 5 times A? Is nothing but 5 lambda 1, 5 lambda 2. 5 lambda 1, comma 5 lambda 2. And what is the eigenvalues of A power 7? Is nothing but lambda 1 power 7, comma lambda 2 power 7. And what is the eigenvalues of A power 10? Is nothing but lambda 1 power 10, comma lambda 2 power 10. Therefore, what is the eigenvalues of A power 10 plus A power 7 plus 5 times A is nothing but just you have to add the first coordinate. Therefore, what will get lambda 1 power 10 plus lambda 1 power 7 plus 5 lambda 1. This is a one eigenvalue. So other eigenvalue lambda 2 power 10 plus lambda 2 power 7 plus 5 lambda 2. This is another eigenvalue. Okay, this is only for all the matrices are A or all the matrices are same matrix. Suppose if you know this is not true for general case. Suppose lambda A have a 2 eigenvalue lambda mu. Suppose B is another B is another matrix. Suppose it has some other eigenvalue. Suppose this is lambda 1 mu 1 and suppose this is lambda 2 mu 2. So we cannot say the eigenvalues of A plus B is not equal to lambda 1 plus lambda 2 mu 1 plus mu 2. This is not true in general. If both matrices are same matrix, then we can add corresponding. So you cannot change the order. So once you fix lambda 1 is the first eigenvalues, lambda 2 is the second eigenvalue for A. For suppose you're finding the powers are multiply, you cannot change the order. So this is the order. Suppose lambda 1 first, lambda 2 first, second. Then 5 times A, 5 lambda 1 is first, 5 lambda 2 is second. You cannot change the order. Okay. So therefore, for this problem, first you got to find the eigenvalues. And then you have to check if all the eigenvalues are distinct, then we can say it's a diagnosable. Otherwise, how to check is a diagnosable or not? You have to find the corresponding eigenvectors. We get a three eigenvectors for each eigenvalue. We have to check is it linearly independent or not. If it is linearly independent, then we can say okay, it is diagnosable. Okay, quickly, maybe we can say what are the eigenvalues. So what is the eigenvalues? So what is the characteristic polynomial of this? A minus lambda I or xi. You can take anything. So determinant of this, so is nothing but 5 minus lambda or 5 minus x. Take x or lambda. Okay, so better I take x. So 5 minus, you have to subtract x only on the diagonal. So 5 minus x minus 4, 4, 12 minus 11 minus x, 12, 4 minus 4, 5. So what is the determinant? So it's nothing but, so we can expand via the first row, 5 minus x times 5 into minus 11 minus x minus plus 48 minus plus 4 times 60 minus 48 plus 4, the last number, into 48 minus 48 minus 4 into minus 11 minus x. Now simplify this. This is equal to 5 minus x into, if you multiply this, we get a minus 55 minus 5x plus 48 plus
Sir,
4. Yeah.
sir, here last element will be 5 minus x only, no, sir? Written only 5, because
Here.
diagonals we have minus.
Which one?
The diagonals, sir, 5 minus x minus 11 minus
Oh,
x.
sorry, sir. Thank you. Okay, sorry. Yeah. So therefore here we get, sorry, here 5 minus x. Thank you. And then any other uh, for this one also. Okay, this position also we have to change. So therefore minus plus 4 into 12 into 5 minus x minus 4 into 12, that is 48. And others are correct, I think so. Yeah, now multiply this. First you got to multiply 5. 5 into minus 11 minus 55. And then 5 into minus x minus 5x. Minus plus 11x. And then minus plus x square. Plus 48. And here plus 4 times. And this is 10, 60 minus 12x minus 48. And here plus 4 times minus 48 minus plus 44 minus plus 4 times x. Okay, now if you simplify and then find the eigenvalues. So this is equal to 5 minus x times, we write in the decreasing order, x square, and this is 5x and this is 11x, therefore this should be plus 9. Oh, not 9, 6x. Now this is 48 and this is 55, therefore should be minus 7. And here plus 4 times minus 12 times 12x, and this is 48 means 12 plus 12, and plus 4 times 4x minus 4. Okay. Now just to multiply 5x square, 30x, 35 minus x cube minus 6x square plus 7x. Now multiply minus 4 here, minus 48x plus 48 plus 16x minus 16. Now write in the decreasing order, only one x cube, that is minus x cube. What is the x square term? This is 5x square and this is 6, therefore we get only one x square, right? Minus x square. Now what about x term? 30x, 7x, 37, and this is right? Yeah, 37, and then we have 16. So totally 53, but we have a this is a minus. Oh, sorry. Okay, yeah, it's minus 48. So therefore, should be 5 plus 5x. If any mistake, please correct me. So this is 30x plus 7 is 37 plus 16. 37, 47, 53 minus 48. So 53 minus 48 is plus 5, 5x. Now the next term is constant term. So this is 35 and this is 16. Therefore 40, 51 minus 51 should be minus 3. Yeah. Right? So this is a characteristic polynomial. If you take the characteristic equation, this is nothing but a minus xi, determinant of a minus xi equal to 0. This is a characteristic equation. The roots of this is nothing but we multiply x, therefore a minus, therefore x cube plus x square minus 5x plus 3 equal to 0. Now what are the roots? If substitute x equal to 1 is a root. Therefore, we guess one root, 1 is a root. If you go to the synthetic division, 1, 1 minus 5, 3. So we guess that 1 is a root. Therefore, 0 plus 1 is 1, 1 into 1 is 1, 1 plus 1 is 2, 1 into 2 is 2, 2 plus minus 5 is minus 3, 1 into minus 3 is minus 3 is 0. Therefore, what is the corresponding this? X square plus 2x minus 3. Okay. Therefore, what is the root of this one? 1 and 2. Oh, no, sorry, 1 and 3. So therefore, you can write 1 minus x minus 1 into, this time writing it, please wait, yeah, plus. Okay. So x minus 1 into x plus 2, we get this. Because that means the roots are 1 and minus 2. No, I did some, okay, sorry, some 3 will come, right? 3. Correct? Because x into x square, this is plus 3x minus x, we get 2x, and then 1 into 3 is minus 3. Okay, correct. Therefore, this is nothing but, already we found that 1 is a factor. Now we got one more factor is, again 1 is a factor. Now x plus 3 is a factor. Therefore, we get the eigenvalues are 1, 1, minus 3. But here we didn't get a distinct eigenvalues. We get the same eigenvalues, namely 1, 1. Okay. Therefore, we cannot conclude that this is not linear, is not diagnosable. We can find the characteristic vectors. But we can easily say the eigenvalues of the matrix A power 10. So this is the eigenvalues of A. Now what is the eigenvalues of 5 times A? We have to multiply 5. 5 minus 15. Now what is the eigenvalues of A power 7? Now raise the power 7. 1 power 7 is 1. 1 power 7 is 1. 7 is an odd number, therefore minus 3 power 7. So what is the value of 3 power 7 taking 3 power 7? Now what is the values of eigenvalues of A power 10? Is nothing but 1, 1, 3 power 10. Therefore the eigenvalues of A power 10 plus A power 7 plus 5 times A, or just add the corresponding thing. This is 7, comma 7, comma minus 15 minus 3 power 7 plus 3 power 10. So what is the value? So maybe take a bigger number, right? Okay, anyway, just to find that values of this, you will get the eigenvalues of this number. In this matrix A power 10 plus A power 7 plus 5A. So for diagnosable, we have to find the eigenvectors. From that, we can conclude that is a diagnosable. Or anyway, it is diagnosable. We have to show this is diagnosable. There is some other method is there to find to check the matrix is diagnosable or not. If possible, just to go through the book, they mentioned some theorem to find the. So maybe I can say now. Maybe I say the theorem result here. So for each eigenvalue, so we know the multiplicity. Multiplicity means what? How many times it is repeated. Look at this this matrix. The eigenvalues are 1, 1, 2. What is the multiplicity of 1 is 2 because 2 times repeated. Okay. Therefore, the multiplicity of eigenvalue lambda equal to 1 is 2. The multiplicity of minus 3 is 1. So multiplicity is nothing but this number of times repeated. Okay, that is called algebraic multiplicity. So the algebraic multiplicity of lambda is nothing but the number of eigenvalues. So there are two multiplicity. We can say algebraic multiplicity. Algebraic multiplicity of the eigenvalue lambda is nothing but number of times is repeated. Number of times lambda repeated. So the number of times repeated is called the multiplicity, algebraic multiplicity. Now, what is the geometric multiplicity? Geometric multiplicity of the eigenvalue lambda is nothing but dimension of the null space of or the kernel or null space of T minus or A minus, okay, depending upon the, and suppose if we take A, because A is a linear transformation. So null space of A minus lambda I of dimension. So the dimension of null space of A minus lambda I, we define the geometric multiplicity of one particular eigenvalue. So for any eigenvalue, we can talk about two multiplicity. One is algebraic multiplicity, another one is geometric multiplicity. But in our previous case, what is the algebraic multiplicity of lambda equal to the, what is the algebraic multiplicity of minus 1 is 2. Okay, so algebraic, okay, we usually call GM. GM means what? Algebraic multiplicity. So AM is geometric algebraic multiplicity of the eigenvalue 1 in the previous is 2 because it's repeated 2 times. So what is the geometric multiplicity of 1? We got to find it. Okay, what that is, we got to find the dimension of the null space A minus lambda I. Okay. Suppose if these two numbers are equal, then we say for all eigenvalues lambda, the algebraic multiplicity and the geometric multiplicity are equal, then A is diagnosable. Okay. But in general, this is not true. Algebraic multiplicity need not be equal to the geometric multiplicity of a particular eigenvalue. But for all eigenvalue lambda, the algebraic multiplicity and then equal to geometric multiplicity, then we say A is diagnosable. Okay. So A is diagnosable if and only if the algebraic multiplicity and then geometric multiplicity of each eigenvalue should be equal. So that is maybe state as a note, very important note. So A is diagnosable if and only if for any eigenvalue lambda, eigenvalue lambda of the matrix A, the algebraic multiplicity of that particular lambda is same as the geometric multiplicity of the eigenvalue. For any eigenvalue, the corresponding multiplicity, algebraic multiplicity and geometric multiplicity equal, then we say the matrix is diagnosable. But in the previous case, we found that eigenvalue 1 1 minus 3. Okay, 1 1 minus 3. So in that case, what is the algebraic multiplicity of the eigenvalue 1 is 2 because 2 times repeated. What is the algebraic multiplicity of the eigenvalue minus 3 is 1 because it's 1 times repeated. Now we have to find the geometric multiplicity because this is only 2 eigenvalue. We have to check only for 2 eigenvalues. Now we have to check the geometric multiplicity of 1 is what. And then what is the geometric multiplicity of the eigenvalue 3? Okay, if this is 1 and this is 2, then this is diagnosable. Okay, maybe I will prove one thing, and then maybe you take one thing as an exercise. Okay, now suppose I find the geometric multiplicity of, so what I am to do? Okay, suppose I am taking this one. So I'm going to check what is the geometric multiplicity of the eigenvalue minus 3. That means what we have to prove the dimension of and the null space of A minus, but here my lambda equal to 3, right? Therefore lambda equal to minus 3. So what we are going to check what is the dimension of the null space of A minus, but here lambda is minus 3, therefore plus 3 times I. So what is the dimension of this? So what is the meaning of this null space? What is the definition of null space of A plus 3I? Is nothing but we are collecting the vector X. That is why the condition that A plus 3I into X should be 0. We are collecting the solutions of this. We are collecting the solutions of a plus 3i x equal to 0. That is a null space. But here A is a 3 by 3 matrix. Therefore, this capital X and take capital X. Okay. So the capital X may be X, Y, Z or X1, X2, X3. Okay, you can take anything. Now we have to solve the system and then we have to, so maybe actually it's nothing but, so this X contains, maybe you can take X, Y, Z. X, Y, Z such that A plus 3i times capital X. So capital X is nothing but this one. This is a capital X equal to 0. Now here we have three unknowns. Using this condition, we try to remove or eliminate some unknowns. Okay. Now consider this equation a plus 3i x equal to 0. So what is a plus 3i first of all? So we have to sum 3 only on the diagonal. So I'm directly right. So so must I write a. What is a? 5 minus 4, 4, and then 12, 11, 12, and this one is 4 minus 4, 5. This is a. Now what is a plus 3? So it's nothing but directly I'm writing. So 8 minus 4, 4, 12, 14, 12, 4 minus 4, 5 plus 4, 8. Into x, x is nothing but x, y, z equal to 0, 0, 0. Now we have to find the solution. Now it is very difficult to find the solution. Therefore, we have to reduce this into row reduced echelon form matrix. Okay. So better what we have to do. Okay, anyway, we can interchange the third row and then first row. So just I change the rows. 4 minus 4, 8. And then I keep this one is 12, 14, 12, 4 minus 8. We can interchange two rows because we didn't find any determinant. Okay, we just apply the elementary row operation. So elementary row operation says you can interchange any two rows. So this should be 8 minus 4, 4. Anyway, the left hand side, right hand side, we have only 0, 0 column. Okay, if you interchange two rows, again we get 0, 0. Okay, therefore don't bother about the right hand side because we use a 0, 0 vector. Now actually what we are doing here, so we interchange the R1 and the R3. Now what we have to do, we have to form a row reduced echelon form. Therefore the first entry should be 1, but the first entry is here 4. Therefore what we have to do, we have to divide 4 to the entire first row. Therefore we get 1 and this one is minus 1 and this should be 2. Okay, so x, y, z equal to here 0, 0, 0. So what I am doing here, so R1 is nothing but just I multiply by 1 by 4, 1 to the R1. I will keep the second things on 4, 12, 14, 12, and then 8 minus 4, 4. Now what we have to do, we have to make this entry 0 and then we have to make this entry 0, right? Therefore what we have to do, we have to multiply 12 to the first row, we have to subtract. So maybe I can write here, okay? So you can keep the first row 1 minus 1, 2, and then suppose you into x, y, z. The right hand side you can keep 0, 0, 0. Now the second row going to replace, I'm going to multiply 12 to the first row and then going to subtract the second row. So therefore 1 into 12 is 12, 12 minus 12 is 0. And this minus 12 plus, so minus 12 and then we have to subtract, therefore minus 14, therefore minus 26. And here 2 into 12 is 24 minus 12. You get 12. Again the last row, so I'm going to replace the third row by multiply 8 to the first row and then subtract from the third row. So therefore 1 into 8, 8, 8 minus 0. And this is minus 8 and minus minus plus 4, right? Therefore minus 4. And here the first entry is 2, 2 into 4, 8, 16. 16 minus 4 is 12. We get this. Okay, now what we have to do. So now we finish the first row. We scan the first row, we get non-zero entry here, and it should be 1, and the corresponding columns are 0. Now if we scan the second row, we get a non-zero entry, but it should be not equal to 1. Therefore, we have to make that entry is 1. Therefore, we have to divide 26. Therefore, keep the first row. So better I take this only this matrix, okay? So don't write this x, y, z. Finally, I will take. So now the R2 row, what I am going to do, I am going to multiply minus 1 by 26 to the second row. So what we will get here 0, here become 1. This is minus 12 by 26, how much? 12 by minus 26. We can cancel how many times? 13, huh? 6 by 13, huh? Yeah, minus 6 by 13. Now, keep the third row, 0, minus 4, 12. Now, again, we have to make the above the elements, above the this element, we have to make this element 0, this element makes 0, right? So, therefore, just replace the first row by, just add the first row and second row, we have to put in the first row. So, 0 plus 1 is 0 in the first row. So, what I am going to do, the first row I am going to replace by, just add the first row and then second row. So therefore, the 1 plus 0 is 1, and minus 1 is 0, and what is this? 2 minus 6 by 13 is nothing but just to cross multiply. 26 minus 6 by 13 is nothing but 20 by 30. Nothing but 20 by 30. 13. Now we can keep the second row. 0, 1 minus 6 by 13. Now the third row, I am going to replace, multiply 4 to the second row and just add to the third row. Therefore, we get 0, 0, and 1 into this is 0, and this is 4 times 6 by 6 into 13 minus is there, and then plus 12. So how much? 24 minus 24 by 13 plus 12. So how much? So anyway, okay, may I take some number? Okay, so better I take some star. Anyway, you can find. So we get star here, but the star is not equal to 1. Okay, now we take some star. Okay, because we are going to find only the number of things. Now we get. So again, look at the last row. We will not get a. Okay, this is not 1. Therefore, we get to multiply that number by this number. Therefore, we get 1. So no need to find that number. Okay, because that number going to be 1. So therefore 0, 1, 1, 0, 20 by 13. The second row 0, 1 minus 16 by 13, 0, 0, 1, because the entire row we are going to multiply 1 by the star. Okay, now we get a row reduced echelon form. Now we multiply this x, y, z. We get a relation between x, y, z. So therefore, this is into x, y, z equal to 0, 0, 0. Now multiply the first equation, we get x minus plus 20 by 13 into z equal to 0. From the second, we get y minus 16 by 13 into z equal to 0. Finally, we get z equal to 0. Oh, I think we get only 0. Maybe I did any wrong. Maybe I did some mistake. So suppose you get, that means what, 0 is the only solution. No, it is not. 0 is the only solution. Maybe I made some mistake here. Okay, I don't know where I did mistake. So you get some non-trivial solution. So therefore, finally we find the number of unknowns. So here we start with the 3 unknowns. Okay, so using this condition, we will reduce this to maybe everything will get to only 1 unknowns. So therefore, the multiplicity, geometric multiplicity, I think will get to 1. So therefore, we get geometric multiplicity of the eigenvalue minus 3, and then the arithmetic multiplicity of minus 3 would be equal. Similarly, we have to find the geometric multiplicity of the eigenvalue lambda. So you will get the dimensions 2. Therefore, both are equal. So therefore, the matrix is diagnosable. So this is a very important point. A matrix is diagnosable if and only if for any eigenvalues of A, the arithmetic multiplicity and the geometric multiplicity should be equal. Okay, I think in general case, I think so. The relation between this arithmetic multiplicity is always bigger than 1. Is geometric multiplicity of the lambda is less than or equal to arithmetic multiplicity of lambda. So arithmetic multiplicity is bigger than geometric multiplicity. Geometric multiplicity is bigger than 1. Okay, this is always true. But if it is equal for all eigenvalues lambda, that is a diagnosable matrix. Okay, anyway, I stop now. Thank you.